Welcome everybody to our December talk in the Distinguished Colloquium series of Turkish Math Society. Our speaker today is Wilhelm Schlag, a well-known leader in several areas of analysis, including dispersive PDEs, spectral theory, nonlinear math physics, and harmonic analysis. So Wilhelm got his PhD from Caltech in '96 under the supervision of Thomas Wolff. After a few years in IAS and Princeton, he went back to Caltech as full professor in 2001. Later on, he moved to Chicago and more recently in 2018 to Yale. And he's there now, the department chair. He held several prestigious fellowships and was an ICM speaker in 2014. And today, the title of his talk is Asymptotic Stability for the Sine-Gordon Kink under odd perturbations via supersymmetry. So.
Thank you so much, Burak. It's a great honor to speak here at the Turkish Mathematical Society Colloquium. I don't know if I'm distinguished or not, so maybe I'm the wrong choice for speaker. Thank you, Burak, for the introduction. It can only go downhill from here, right? So here is a little introduction. I hope it is not too elementary. Let's start with the equation of the infinitely long vibrating string. V here is the velocity. Let's take it to be constant. This very well-known one-dimensional wave equation is an approximation. It only makes sense. So here is, say, the x-axis, but then we should think of u as being the distortion of this line from zero, from equilibrium. And if u is too big, the string will break, etc. So this is only an approximation. It's also an approximation in the sense that we're assuming that the string is completely homogeneous, so that v is constant. If the material changes along the string, then our velocity would have to be a function of x. Be it as it may, it's very well known how to solve this equation. So we simply observe that we can factor the left-hand side dt squared minus v squared dx squared in this fashion. All right. And now we look for solutions of this separately equals 0 and that equals 0. So I shouldn't make a mess of everything. And we find that these are just transport equations, but we don't even have to know what they're called. You immediately see that these these first order problems are given by respectively x plus t, functions of x plus tv and x minus tv. L is left moving, R is right moving. And because of the linearity of the problem, we can just add them up. Now, at this point, it's not clear if we might have missed any possible solutions, but in fact, all solutions of the so-called Cauchy problem, where we assign data here at time 0, you have initial position of your string, initial velocity. And that's all you can hope to prescribe, just in Newtonian mechanics, F equals ma. And so you have this extremely well-known Delam Bare formula. And we can also look at this a bit differently. It's very common to decompose, or not decompose, to introduce these characteristic variables. So x plus vt and x minus vt. If you do this, and they're already hidden here, of course. They're hidden if you want here and here. These are the two characteristics. This would be del psi, this would be del eta, or the other way around. And so you see that your entire wave equation becomes that, and you can separately integrate in eta and then separately integrating c, which is what we did here anyway, all right? So now, as simple as the equation is, it's not to be underestimated. Even the one-dimensional equation has some remarkable symmetries, conservation laws, and so on. So note that you have conserved energy E, conserved momentum P. Again, this is a Newtonian theory, if you want, albeit in continuum mechanics. So we're integrating here, of course, from minus infinity to infinity, which is an idealization. There is no such thing as an infinite string, right? But that's all right. So better than these numbers, dealing with the number big E, the number big P, it is to think of this locally in space and time. And to do this, we note that the space-time divergence, or rather time and space divergence. So what this means, of course, is ET minus PX, all right? That equals 0. Where E is the energy density, P is the momentum density. And what could be more natural than to integrate this divergence, which is 0, and apply the divergence theorem? But the question is, on which region do we integrate this? And the region I drew on the following page, it is this trapezoid. So essential for this trapezoid is that the sides are characteristic. So I picked here the velocity equals 1. So my characteristic variables psi, I forgot whether I used them plus or minus here, x plus t, eta is x minus t. So here that has to be 45-degree angles. That is essential. Why is that essential? Well, look at this little calculation we did here. So take the divergence, integrate it over the boundary, then of course you get the integral over the boundary where you dot this vector field E minus P into the normal vector. So here I drew a few normal vectors on the top side. This is a time-space picture. So 1, 0, minus 1, 0, and so on. So the upper side gives you, the upper horizontal segment gives you this, the much bigger lower horizontal segment gives you that. And here are these two characteristic pieces. This would be gamma left, that's gamma right, okay? And what's so remarkable here is that E plus P, look at E plus P. This is UT plus UX squared. And E minus P is UT minus UX squared. And so these are complete squares, greater equals 0. And there is a very clear reason why this is so, because the characteristics look like this, so they look like that, and the other ones, they look like this. So you see, because the angle is exactly 45-degree, you cannot have what I'm drawing here. You cannot have anything entering the trapezoid from outside. Therefore, the only thing that can happen, so this is forbidden. If you change the angle, of course, if you make it bigger, then you have a problem. Then the characteristics can enter. But what we've proven now is that the energy computed over this has to dominate the energy over that. So it can only decrease, this energy is decreasing. And this has profound consequences. For example, if the data are 0 here, then everywhere here, the solution has to vanish, okay? This is exactly finite propagation speed. So you have domain of dependence. If you are in space-time, the solution here only depends on the data there. If the solution vanishes everywhere here, then, sorry, if the data vanish everywhere here, the solution will vanish everywhere, okay? So that is an elementary observation. Now, a more realistic, if you take a typical string, it has finite length. So you have, in addition to the wave equation, boundary conditions. For all times, you have to be fixed at 0 or at L. Now, it's quite remarkable. You can do this using the Delam Bare solution for the whole line, but you have to say you'd start with initial conditions like this and 0 initial velocity. Then you have to make an odd extension and it becomes 2L periodic. And just to show you what this looks like, I have this silly little this here. You see, so red moves to the right, blue moves to the left. You add them up, you get green, which clearly is a vibrating string on the interval 0, 1. Okay. So now, obviously, a different way to approach this is to decompose into the harmonics of the Laplacian, the eigenfunctions of the Laplacian on the interval 0L, and here they are. And then you have a time-dependent coefficient which satisfies the equation of a harmonic oscillator. You solve the harmonic oscillator, you plug it in, you use addition laws for sine cosine, you get exactly the animation back that I had before, which is nothing other than the addition of a wave that moves to the left, a wave that moves to the right. Energy conservation follows from Plancherel. Fourier himself started with the heat equation on a ring and amazingly introduced this idea, which, if you want, is an idea of the ancient world, that everything should be a superposition of some kind of harmonics, just like the Greeks philosophized that the planets followed special geometric shapes. Everything was supposed to be built up from simple things. Little did they know that, you know, this is actually correct in some shape or form, but it took a long time to work out. The heat equation is not realistic, but because it has infinite propagation speed, so it's clearly an approximation. And here I couldn't resist to remark how from the wave equation we went to the Fourier series, and what could be more influential than this idea of building up from harmonics. You know, number theory, automorphic form, Selberg trace from the Langlands program, which I'm not part of, obviously. But then in applications, electrical engineering, these wonderful devices. This is applied Fourier analysis. Okay. Now, so far, the wave equation of the string was an approximation. Continuum mechanics, small elongations. If the elongations are too big, the string breaks. Now, of a completely different nature are the Maxwell's equations, which I just put down here. B is the magnetic field, E is the electric field. And this is what Maxwell did. First of all, he got it right. Delam Bare's law, Faraday's law, he added the so-called, it has a name, displacement current. Okay. And then he observed what kind of notation he used is beyond me. I think he wrote everything down in components very patiently. And if you use this, so you differentiate this equation again in T, you plug in the second one, then you get that, and symmetrically you get this. And what still kind of shocks me is that the fact that light is an electromagnetic wave was discovered by Maxwell by pen and paper. So that shows you the power of mathematics, doesn't it? And the way he did this is that he actually had physical constants in the electromagnetic equations. In the E equation, B equation, it was a dielectric constant, a diamagnetic constant. He knew them from roughly, experiments had been made to measure them, and the speed of light was approximately known. He plugged in his constant and he got c squared. He got, for the value of c in physical units, something that he immediately recognized as the speed of light. And so how amazing is that? And notice that the wave equation here is not an approximation to anything. It is fundamental. And as you know, it gave rise, because of the constancy of c, this was such a difficult concept to accept first, that the speed of light is independent of the source, the velocity of the source, and the frame from which you observed. And if you accept that, and you dismiss this idea that there is some kind of ether propagation medium, then you have to arrive at Einstein's conclusions, you know, including E is mc squared, which is oversighted. All right, and I couldn't resist to put down this very well-known picture of E and B. So the moving E field generates B, the moving B field in turn generates E, and this whole thing propagates. So enough of this introduction now. What we're going to talk about is not linear models, linear partial differential equations, but nonlinear ones. And somewhat surprisingly, one-dimensional nonlinear ones. Even in that case, there are, to this day, open problems that really seem very difficult. And I'll try to tell you what kind of open problems there are. But let's start with really a Hamiltonian model in infinite dimensions. It's Hamiltonian mechanics, if you want, in infinite dimensions. You start from a Lagrangian, which is written up here. This is L. W will be your potential energy that will come up in a second. You can think, for example, if we will do this, the potential energy of the pendulum, 1 minus cosine phi. So you look at the Euler-Lagrange equation. It is the equation of motion. On the left-hand side, you recognize what we had on the first slide, the wave equation. Okay? And then you have a conserved energy, just like we had before. But the difference is now going to be that we shouldn't think of data that are, say, compactly supported, because our data might not even have finite L2 norm. In fact, that is precisely the kind of situation we're interested in. But not to get ahead of myself, for W, the potential energy, let's look at two specific examples, both very famous. These models, this is called classical one-dimensional field theory. I don't know when it was first formulated in quantum mechanics, and you can do this in higher dimensions, in 3 dimensions. Then the kinks that I'm about to talk about are called domain walls. And you will see that over the past 10 years, if you just search the internet, many physics papers and books have been published on this to this day. And it's very hard outside of the completely integrable case to prove things. So here is the potential energy of the physical pendulum. And the double well, which is this picture here, is 1 minus phi squared squared. And if you look at the PDEs, you get these astonishingly beautiful equations, non-linear, of course, this and that. And we are only interested in solutions of finite energy. For example, somewhat shockingly, if you put 0, right, the 0, phi equals 0, identically 0, of course, solves this equation. This should be the trivial solution, but actually it's a forbidden solution because it has infinite energy. W of 0 is a quarter, I suppose. Then you're trying to integrate a quarter of the whole line, you get infinity. In contrast, for the sine-Gordon model, so for some form of quantization of the physical pendulum, the 0 solution is completely admissible. It has potential energy 0. So speaking of the double well now, we of course understand that these potential wells, the phi minus, phi plus, which for phi 4, this would be -1, this would be +1 for phi 4, they are nice solutions, constant in space and time, and they have finite energy. In fact, it will not surprise you that all solutions of finite energy have to fall into either of these wells. For sine-Gordon, you have infinitely many choices of such constant solutions, all right? So these are the so-called vacuum solutions of finite energy, and they're all stationary meaning time-independent solutions of finite energy, which are also constant in space. Now, more interesting, perhaps, are the solutions which are constant in time, but not space. And what you see here is the phase portrait. They are, of course, solutions of this ODE, okay, this ODE, which is very easy to solve. All you have to do is you multiply both sides by k prime and you integrate. If you do this, you will get, what is it, 1/2 k prime squared minus w of k equals a constant. Okay. And then, of course, if you want finite energy, this should go to, K prime should go to 0 as x tends to infinity. And WK should go to 0 as x tends to infinity. So the only allowed constant here is 0. And so then you get these explicit expressions. You can integrate. This is just a separable first order ODE. In the phase portrait, what we're talking about are the heteroclinic orbits connecting the equilibria, connecting the potential wells. So you would, the kink, this is this object we're so interested in here. Here's a picture of a kink. It connects phi minus to phi plus, and it will be important for our theorem that I'm going to state later that this is an odd solution. So you use the symmetries in X, okay? Please interrupt me at any moment with questions. Now, we had Maxwell's equations a moment ago. As in Maxwell's theory, you can talk about a current here, and the current satisfies, and again, we saw these types of conservation laws before, it's continuity equation. Exactly as before, we have a space, rather a time-space divergence vanishing for this vector field J. The fact that this vanishes is trivial. It's phi tx minus phi xt is 0. And so you define a charge, and the charge is the integral of phi x from minus infinity to plus infinity. Well, phi x lies in L2. We assume that that means it tends to a constant at the ends, right? So you get that you have this charge in terms of the field phi. And this is conserved if you use your divergence in Tx of J is 0. In other words, just the equality of mixed partials, you move the T derivative inside of the charge, you immediately get that you can integrate. You get J1. J1 is phi t minus phi t, should lie in L2. Well, L2 should mean that you tend to 0 at infinity. So that's 0. And so this charge splits the solutions of finite energy into sectors, if this is what you want to call them. We're in infinite dimensions. So the vacua, meaning these potential wells, which are constant in space and time, have 0 charge, of course. Kinks and anti-kinks, these are the two heteroclinic orbits I had in the red heteroclinic orbits I had. You have charge plus minus 1. Okay, and for sine-Gordon, similarly, you have for the kinks plus minus 1. Somewhat remarkable is that you can achieve all integer values of the charge for sine-Gordon, but not by time-independent solutions, only by gluing together kinks, anti-kinks, which will then start moving according to Newton's law. So if you just take a kink, you move it very far to the left, and another kink, you move it very far to the right. You can't just add them up, because this is a nonlinear. Both models we had, phi4 and sine-Gordon, are nonlinear. They don't have the superposition principle. But nevertheless, they will be close to solutions, and you can show by various means, much harder for phi4 because it is not completely integrable. But if you use methods of inverse scattering transform for sine-Gordon, you can show existence of any kind of multi-kink, anti-kink solution, which realizes these different values of charge, and they move in time, okay, and not stationary. So what, of course, is of interest to physicists, perhaps less so, but then to mathematicians, is this whole question of stability. So orbital stability is always much easier in a dynamical system if you have, say, an equilibrium here, and then you have a trajectory like that, that's stable, okay? It's an elliptic point, stable. And you have the theory of Lyapunov functionals, which just means that you're trying to find, so now I'm changing my story a little bit, that the blue lines will be now level curves of a function of two variables in this case, and then you want your vector field to point inwards everywhere. Possibly it can be tangent, but it can never point out. If it points inward, clearly you're trapped. Then every trajectory has to fall into, remain inside, not necessarily fall into, but remain inside of these blue curves, and the function that has the blue curves as level curve is called a Lyapunov function. Here in infinite dimensions, you can still use such ideas. And for example, this is for sine-Gordon, what I wrote down there. The zero solution is orbitally stable, and you can use the energy basically as a Lyapunov function. Asymptotic stability would mean that in addition, your trajectory has to converge to the equilibrium in infinite positive time. You can reverse time, of course. And so what this means in the infinite dimensional context here is that we are trying to find some topology, some norm, in other words, so that phi and phi t together tend to zero. Now notice that in finite dimensions, the topology never matters because they're all comparable, but in infinite dimensions, this is hugely important. It defines really the issues. One reasonable choice is that's called global asymptotic stability in this context is the L infinity norm. And then what you can try and do for sine-Gordon, remember what is sine-Gordon? It's this equation, phi tt minus phi x plus sine phi is 0. You can Taylor expand sine phi, you get phi and then a cubic term. And it doesn't sound unreasonable, right? To just keep from sine phi phi and throw away the cubic term. Now it will turn out that this is exactly a key difficulty. It's hugely, the cubic term is long range and you precisely cannot throw away that cubic term. You can throw away the quintic term, move it to the right as a perturbation. Nevertheless, we should start somewhere here and solve this Klein-Gordon equation. That's what it's called. Notice we had before that we started on the first page with UTT minus UXX, V equals 1, right? UTT minus UXX. Now we're modifying this. We have UTT minus UXX plus U. And that is the Klein-Gordon equation. And amazingly, it has, the solutions will decay in time. If you take nice Schwartz functions or whatever, compactly supported functions with some regularity, typically we want Schwartz functions. Then they decay at a certain rate. In complete contrast to the wave equation, this doesn't decay at all. Doesn't decay. It's just two bumps that move to the left and the right. But if you add this term, this plus u, then the waves will decay. And there are a number of ways of looking at this. You no longer can play the tricks we played before, and the phenomena are fundamentally different. But you can't just separate this into two pieces, otherwise where would the decay come from? So one thing you can do is you write this second order equation as a first order system. You obtain a matrix operator, J is a symplectic matrix, H is a symmetric matrix, the Hamiltonian in fact. And conserved energy in this formalism is quite nice because if you call this vector big U, then the conserved energy is simply 1/2 for cosmetic reasons, and then big U, H big U. And if you differentiate E in time, what you find is that of course you get U dot, but U dot is what? It's JH, JHU, HU, and then you have the second factor U, H, U dot is JHU. But you see, if you move this JH to the other side, this here or vice versa, then you get negative J, so E dot is 0. That's exactly the Hamiltonian trick with P dot is minus HQ, Q dot is HP, so H is conserved. That's exactly this. Be it as it may, you can explicitly compute this matrix exponential on the Fourier side, meaning that if you Fourier transform this equation, you of course run into 1 plus psi squared u hat, so you get u hat tt plus u hat is 0, and then you solve, and that's exactly what you encounter here in this matrix formalism. Omega is the so-called Japanese bracket. This is Japanese bracket. It's called Japanese bracket even in Japan. D is the momentum operator. Omega is the Japanese bracket of the momentum operator. On the Fourier side, it's multiplication by Japanese C, all right? And now the Delam Bare solution, which we started with on page 1, has no decay at all, left and right moving wave. But this does have decay. And in principle, this is an exercise in stationary phase. You, of course, have to get that decay from somewhere. And you see here, the main term is exactly what you get by pulling stationary phase off of the shelf. So Barak mentioned that both he and I are students of Tom Wolfe, and Tom Wolfe really loved stationary phase for a number of reasons. And you can just take volume 1 of Hermanda and you see how it works there. You compute the leading term, this is what you get. On some level, the reason that the wave equation doesn't have decay is because its characteristic variety, which is the space-time Fourier transform, basically the symbol of the wave operator in one dimension is a pair of lines. Okay. But the symbol of the Klein-Gordon equation is better behaved. It's tau squared minus psi squared minus 1 equals 0. And that's a pair of hyperbolas. Trying to draw a pair of hyperbolas, and they have non-zero curvature. However, the curvature decays, of course, as xi tends to infinity, and it decays like an inverse cubic. This is 1 over the root of the curvature. And then you plug in the critical point of the phase, which I compute here. Rho is the Minkowski metric. Of course, it only makes sense in the light cone. Well, that is finite speed of propagation. Okay, that is finite speed of propagation. You cannot expect to have this leading order decay outside of the light cone. So that's that. That vanishes if absolute x is outside, if it's, well, if you pretend that the picture I drew is in xt, then you would be here, but that's cheating because that's the dual picture in the Fourier variables, okay? So then the leading order term vanishes and you're faced with the decay outside of the light cone. So this here is not just something you take off the shelf from Hermanda, whatever. You have to use a little bit of estimation of oscillatory integrals, but nothing sophisticated. You just work a bit and you find that by integration by parts, interpolation, other tools, you have that. What I want to emphasize are 2 aspects. This, of course, has to decay faster than the leading 1 over root t, and you only have 1 power of x here on the right. And you happen to have 2 derivatives, which I'm less afraid of, but this 1 weight of x, for the experts, what you have to really worry about is when you study the full nonlinear evolution, you apply vector fields, and you apply specifically here, because of Lorentz invariance of the problem, the generator of Lorentz transforms, which we call it L, is x dt plus t dx. That is the infinitesimal generator of the Lorentz transforms, which preserve these hyperbolas. And in fact, the whole foliation of hyperbolas. The Lorentz transforms are precisely the linear group, the group of linear transformations preserving not just the pair of lines, but each of these hyperbolas. And their infinitesimal generator looks like that. And because of this x here that comes up, if you want, through the harmonic analysis, you then have to worry about this as it affects the entire nonlinear flow. And not surprisingly, you try to commute this vector field L through the whole flow, there are error terms, and you don't want to be in a situation where you have to apply 2 or 3 copies of that L. So there was a little bit of a technical digression. So there is a theorem, 20 years old, basically. Delors was the one who started these long-range, one-dimensional problems that had not been really studied carefully before him for the wave equation. And be it as it may, he said that for small, that's the epsilon here, for small data in this space, notice this x here, that x is the same as this x up there. The solution decays like the free one, 1 over root t, that's the leading, I should stop making a mess, the leading order decay. But it is completely misleading to think that the free Klein-Gordon captures the asymptotic profile of the wave phi, the nonlinear wave phi, because of this. And to appreciate this point, let me point something out. What was our sine-Gordon equation, but now expanded to third order? So you will then have plus sine phi, so we keep the linear term, but then let's retain the cubic term and ignore the rest. Or we just write big O, doesn't fit anymore, big O of phi 5. And so why am I not afraid of phi 5? Because if you take the 5th power of 1 over root t, this will decay like t to the minus 5/2. That's very integrable in time as you go to infinity. We're interested in infinite times here. But if you look at phi cubed, you will immediately recognize a problem, because if you write phi cubed as phi squared phi, then that decays like 1 over t times phi. But 1 over t is logarithmically divergent if you try to integrate it to infinity. And this logarithmic divergence means that this is no longer valid. This asymptotic description that the free wave gives you is no longer valid. And what you run into is you have to accommodate a logarithmic correction. There is e to the I log t, but times a function w, and you will see it come up in a moment. So this logarithmic phase correction is caused in some ways, but of course the heuristic argument I gave you is much too simplistic. It doesn't explain why you only have a phase correction. But if you're familiar with the long-range correction, in the Moller wave operators and Schrödinger operators, you have the logarithmic correction there too, okay? Modified wave operators. Now, the talk is really not about the vacuum, it's about kink. So what happens if you linearize about a kink? It means that you look for a wave that is the sum of the kink k plus u. Well, if you just expand everything, you end up with a PDE like this. On the left-hand side, you will now run into a potential. Okay, because there is a contribution to the linear term, right? If you take, for example, the cubic power of this, you will run into a term 3k squared u. So that 3k squared produces a potential on the left. And so everybody in this game would start with the linear stability. So what's the spectrum of the Schrödinger operator minus del x squared plus v plus m squared? So what is the spectrum of this? And so if you linearize about the kink for sine-Gordon, and of course you have to make sure that the kink doesn't start moving. And here the symmetry comes in, I alluded to before, k is odd. If you perturb k by an even u, then the Lorentz symmetry will be excited and k will start moving. And then you run into k x minus tv divided by root 1 minus v squared, the Lorentz transformation of k. But v itself might be, or typically is, a function of time. Okay, so we are absolutely avoiding the moving kink in this talk. And so we want odd perturbation. Here is the spectrum of the sine-Gordon linearized operator. It has a ground state at 0. The continuous spectrum starts at 1, and there is no discrete spectrum otherwise. it doesn't have an eigenvalue at 1, it has a resonance at 1, tanh. Tanh is not L2. There cannot be an eigenvalue at the edge of the continuous spectrum in 1 dimension. The ground state, sech, it's clear that there has to be such a thing, because if you linearize, so if you differentiate, look, H, S, G, K prime has to be 0. That is the infinitesimal version of translation invariance of the nonlinear problem. And K prime, tanh prime is sech, I'm using the wrong sech squared, but for sine-Gordon, the kink K is 4 arctan e to the x. If you take an x derivative of this, it's very easy exercise, you get a multiple of sech. So that's the infinitesimal form of the translation symmetry. For phi 4, the picture is more complicated. You have an eigenvalue at 3/2. Again, you have, now we have sech squared. Sech squared is tanh prime, okay? And all of these functions are functions of x over root 2. This doesn't need to excite us. This, the eigenvalue at 3/2, doesn't have a good explanation. It doesn't come from a symmetry, and it's an incredibly delicate thing, because that means on the linear level, you will have a harmonic oscillator. On the linear level, if you have a positive eigenvalue, it will simply lead to a harmonic oscillator. It will oscillate in time and never decay. But then how are you supposed to prove asymptotic stability? Well, that's a whole story. Now, explicitly written out, you obtain very famous linearized operators, namely Peschel-Teller type operators. So the linearization of sine-Gordon is minus Laplace minus 2 sech squared plus 1. For phi 4, you have that. And then you can look at the so-called Yost solutions, which are the solutions that are asymptotically equal to the free ones. This is at x tends to plus infinity. This is at x tends to minus infinity. And they have this beautiful explicit shape. These operators are both reflectionless. So the reflection coefficients are identically zero-fold energies. And they admit a diagonalization, not by the free Fourier basis e to the ix psi, but by this. And notice the discontinuity that happens at psi equals 0. This discontinuity is caused by the threshold resonance. That is the resonance at 1. Well, here the threshold, of course, is moved because we look at the operator minus 1. So therefore, the discontinuity happens at 0. And here is just a brief reminder what that scattering theory looks like on the line. So you're looking for these Yost solutions. As mentioned, they are the ones that asymptote to the free waves, the free plane waves. They're outgoing, incoming, e to the plus minus ix psi. The Wronskian never vanishes for energies different from 0. The reflection transmission coefficient mean nothing other than here is your potential. You send in a wave, part of it gets reflected, part of it gets transmitted, okay? And what is a zero energy resonance, a threshold resonance? It means that the Wronskian at 0 is 0. It means the transmission coefficient of 0 is not 0. Or it means these are all equivalent. There exists a non-zero bounded solution of the eigenvalue problem at 0, but it is not an eigenvalue. It cannot be, okay? Because it has to asymptote to constants. And a resonance simply means that you can glue these two constants together to form a global solution. But resonance, think of the Tacoma Bridge. Why did it collapse? Because you have a harmonic oscillator on the left and the wind somehow managed to blow, I don't know how, with exactly the same internal frequency as the bridge had, one of the infinitely many, the ground state probably. And then you're dividing by 0 and the solution blows up. So here is your small denominator, small divisor, and this is, but it is rank 1. Phi tensor phi, that means if you apply this operator to a function, you get phi integral phi f. That's what phi tensor phi means. And this is well defined provided f is in L1 because phi is bounded. You can't, this is not well defined as an L2 projection. Doesn't make any sense. And this looks really strange if you see it for the first time, that you have to split between psi positive and negative. But the reason you do this is so that afterwards you have this tensorial identity. This is the essence of it's the essence of many things here. It's the essence of definition of Fourier transform, the inversion theorem, invertibility theorem, Plancherel, it all comes from this identity. Now, here's the theorem that we proved with Jonas Luehrmann. He's at Texas A&M. It says that the kink is asymptotically stable under small odd perturbations. The fact that there is an x here is exactly what I spoke about perhaps too long before. It's this x weight you pay in your linear stationary phase type estimate. And it says that asymptotically stable, what does this mean? It means that if you take your wave and you subtract the kink off, of course, this only makes sense if u is odd, if the whole solution is odd, and we're using the kink is odd. Then you have the 1/root t decay. But if you are interested in the asymptotic profile, then you get this, and this looks a little bit scary. There is a reason that we have an integral in space. But if you now pretend the integral isn't there, why can you do this? Look at this kernel. It really lives very near the diagonal x equals y. Meaning that away from this diagonal, the kernel decays exponentially fast. So if you just pretend that this is evaluation at x equals y, you will recognize many things. You have again the cutoff to the light cone. This would then mean absolute x less than t. Well, in this case, it means absolute y less than t. And here, for the first time, you see this log correction coming from the cubic term in the phase. E to the I rho again is the Minkowski metric. This factor we saw before from stationary phase, e to the I rho from stationary phase. This is completely not from stationary phase. This is a nonlinear effect. And what's important is that the error you make decays faster than the root t decay. Now, if you were to try to prove this asymptotic stability in energy alone in H1 cross L2 without weights, it's completely false. And it's false because sine-Gordon, due to its apparent completely integrable nature, has a whole zoo of solutions, including wobbling kinks. So arbitrarily close to the kink in energy, you will find these so-called wobbling kinks, which do this. Here is a kink, and the wobbling kink will just oscillate back and forth between the kink. Orbital stability is a much older phenomenon. What's the point of this theorem? The point of that theorem is we did not use completely integral methods. We used perturbative PDE type methods that I might not have the time to elaborate. Why? Why are you interested in this and not just use completely integral methods? Well, because phi-4 is not completely integrable and it's harder than sine-Gordon. So it's natural to first develop methods for sine-Gordon and then look how to perhaps address phi-4 by similar perturbative methods. So further comments, we don't know how to do moving kinks at the moment, should be accessible by similar techniques. Let me go very quickly here. You can just browse these. I will send you the PDF of these slides if you're interested. They're amazingly only in 2020, Chen-Liu Lu published a proof of asymptotic stability of kink for all data using inverse scattering transform, even though this could perhaps have been done, decades ago. It was done just last year. For phi-4 FGR, I didn't write out what this means. This is Fermi golden rule. So there's this remarkable phenomenon that leads from no decay on the linear part for the harmonic oscillator. I mentioned to you, you have an eigenvalue of 3/2 for linearized 5/4. It does not decay, it just oscillates. So why on earth is the internal mode then on the nonlinear level supposed to decay? Because of a coupling mechanism, again, a resonance, meaning some form of small device between that internal mode and the continuous spectrum. It's a purely nonlinear effect. Okay. Let me just move on quickly. There is something remarkable going on here, and it's the only reason that we can actually prove this. It's the fact that the quadratic term is non-resonant. Again, resonance comes up here as a term, a buzzword. What does it mean in this context? It means exactly that some small denominator does not affect you too badly. It cancels out. Okay, how do you see this phenomenon? And by the way, I was emphasizing at length the danger coming from the cubic term, but this should surprise you because the quadratic term is much more dangerous. It decays more slowly. Not only do you have a log, but you would then have 1/√t times u if you linearize. And that is catastrophic because 1/√t grows if you integrate it like √t. Complete source, apparently a source of instability, total instability. So then how can you prove stability with such a quadratic term? Well, the answer is you remove it by some kind of normal form, like in dynamical systems. And very quickly, to see that phenomenon, you look at this is the quadratic term, alpha is nicely localized for us at the moment. And then you set x equals 0, and you note that at least on the linear level to leading order, this is free Klein-Gordon, the solution behaves like that, e to the plus minus it divided by √t. You plug it in here, you replace that u squared by u lin squared, and you generate that. Then you go into the Duhamel formula, and you get this, right? This is the Duhamel formula. That's the Fourier transform of the solution operator for free Klein-Gordon, and here is this quadratic term Fourier transform. You will immediately see that the S integral here, just look at S, you get up there S times 2 minus Japanese psi. And if that is 0, then you're integrating 1/s ds. Well, that diverges like log t, unless, of course, alpha hat of plus minus √3 is 0, because that's the precise value where Japanese psi is 2. Japanese plus minus √3 is 2. And if alpha hat plus minus √3 is 0, then you can integrate by parts in S, and you do not run into, you don't divide by 0. To this day, we don't know, and this is a very relevant problem, what to do if alpha hat plus minus √3 is not 0, does not vanish, and you have a constant, if you want, cubic term, because then there is this, we just don't know, seems very complicated. Well, let me stop here. I had a few more slides, but let me stop here, thank you.
You were going fine. So let me ask you, so your title mentioned supersymmetry. Maybe you can say a few words about that. Where does that come from?
So what is supersymmetry? Yeah, thank you, Barak, for reminding me in the title there's supersymmetry. It's this thing. So when you, as I mentioned, when you linearize around the kink, you run sine-Gordon, but analogously 5/4, you run into a left-hand side that looks like this. It has a potential. So then it won't surprise the experts, either in PD, harmonic analysis, to hear that a natural attempt is to use the distorted Fourier transform, which I spoke about, for the left-hand side. And Luehrmann and I tried that. The difficulty you have that nobody has been able to deal with for 20 years. This sine-Gordon theorem was kind of, the community, Delors and Masmoudi, etc., were working towards that, but nobody could deal with the threshold resonance. Why? Because the distorted Fourier transform is discontinuous at 0. And so Luehrmann and I tried this with our methods that allowed us to incorporate the zero energy resonance, but then you have to divide small energies from large energies, and you get into horrendously complicated technical issues. But there is something fairly old that you can do here, but has basically never been done before in the dynamical context, in the time-dependent context for this problem. And what is it? It's the fact that you can factorize this Peschel-Teller operator. In fact, this has nothing to do with the specific algebraic form of this thing, into a first order operator d star. D star, of course, is minus del x minus tanh x, and del is del x minus tanh x. And there is a reason you do this, because if you call this y, say del xk, remember that is the infinitesimal form of translation invariance. Of course, this is the operator h, that's the operator h of y, meaning k prime is 0. That's infinitesimal translation invariance. So what you look for now is a first order operator that does the same, that annihilates y. Well, it's of course of the form del x y inverse y. That's your del, or del star. Okay, and then del is minus y inverse del xy. And clearly del star of y is y del x1, but that's 0. So you have just immediately come up completely naturally with this first order operator that annihilates y. And then because h is non-negative, it is fairly clear that h has to be of this form. You can just accept that. But what's so remarkable is that when you flip them, why would you flip them? Well, that's a good question. The magic that happens here is that you then completely kill the potential, that you get v equals 0. You get minus del x squared plus 1. And that has this fancy name of supersymmetry. Thomas Kappeler asked me last week when I gave such a lecture at ISAM near Brown, why this is called supersymmetry. That's a good question. It's just ingrained kind of in the literature. But there is also a book fairly recent by Fritz Wegner, a theoretical physicist, quite well known, who wrote this book about supersymmetry. And it, of course, has all the aspects you expect. So Grassmannian non-commuting variables, supersymmetric replica, what people do in Anderson localization and disordered systems, has nothing to do with this little trick. But then embedded somewhere in the middle are 2 pages where he does that. So I feel comfortable following the convention of calling this supersymmetric factorization. And what this means for us is that we then said, well, why don't we apply the operator d star to the whole PDE? So you don't work with the old unknown u, you work with a new unknown u, namely d star u. And the left-hand side is much easier. The price you pay, of course, is the right-hand side is more complicated. But we do rely on the specific algebra of d star very heavily. We rely on the specific form. And we've spent months trying to play similar games for 5-4. Very difficult and perhaps completely misguided. I admit that it could be, first of all, you have to apply. So my look at all the slides I couldn't do. The outlook is that there's an entire hierarchy of these Peschel-Teller potentials. And 5-4, you would have to apply this supersymmetric trick twice. You would have to flip twice. So you have to differentiate your original PDE twice. And I'm no longer convinced that this is necessarily the correct way to view it. We might as well use the distorted Fourier transform. It's also complicated, but seeming to me, it seems much nicer. But that doesn't circumvent at all what the main difficulties are. And that is the interplay between the quadratic resonance that is caused by the internal mode, the eigenvalue by 3/2 on the one hand, and the cubic terms on the right-hand side on the other hand, both of which lead to some kind of logarithmic correction. We do not know how to play these two off of each other. The key
the normal form, sorry, the normal form transform you apply after D star.
So yes, normal form after. And why can we use normal form? Because this function, look at this explicit function. This is for sine-Gordon. 3 such cube tanh squared. If you compute its Fourier transform, it vanishes by plus minus √3. Isn't that funny? And how do you see this? People in Brown ask me, how do you compute this? Well, you can be very patient and do a residue calculation, or like us, you ask Mathematica to compute the Fourier transform. You wait for 2 minutes because it's struggling, and then you get a formula that has a factor psi squared minus 3. Isn't that amazing? Times all this other stuff. And then Kapila made a very interesting comment after my talk. He said that in the 80s, this was a problem posed by Jürgen Moser. And I have to first understand these papers, which he then sent Luehrmann and myself, is that this is a general phenomenon somehow of completely integrable problems, that if you look at the quadratic term and you linearize about a special orbit, like our heteroclinic orbits, then you don't have a quadratic resonance. And this was completely new to us. We just viewed this kind of as a standalone fact that's, without this observation, you are hopelessly lost. You need this vanishing in order to avoid the small denominator, to avoid the quadratic resonance, and write down a normal form. Here is the normal form. That's the quadratic correction that you add to V. So you don't work with V, which is this complexified wave. You work with V plus BVV. And in this way, you eliminate the quadratic term completely. And here is the small divisor, which is a monster, but alpha 1 hat vanishes where the monster is 0. So therefore, the monster is actually a lamb. Okay, nice lamb. And for phi4, this cannot happen because otherwise the Fermi golden rule would not apply. So you have this, you must have a non-vanishing in order to couple the internal mode to the continuous spectrum, but then you can't apply the normal form for the quadratic term. You can't have the cake and eat it. Yeah.
So although you are not using complete integrability in some sense, of course, it's there.
Yes, that's a very important comment, Barak, and you can criticize us for that. It's true. For in some way that we don't understand, the complete integrability is in the background. And even though we don't use infinitely many conservation laws, we don't use lax pairs, we don't use Backlund transforms, whatever, we use perturbative methods. But we can only apply our normal form because of this vanishing, and this vanishing is some remnant of complete integrability, okay? So, yes.
Okay, thank you. Are there any questions?
If you look at this operator and you have the D star D and the DD star, and
Yeah.
when you commute them, then I think the spectra of DD star is the same as D star D except for 0.
Correct. And you see, thank you, Dirk.
So that also shows you have this really complicated minus dx squared sech squared something, but then the spectra except for 0 are the same as the one where you have a shifted second derivative.
Yes, and not just are the spectra equal up to 0, and I'll talk about 0 in just a second, but both operators have the threshold resonance. You cannot, look, this has a threshold resonance here. The free one has a resonance
at 1.
At 1, because the constant function 1 is your resonance.
Yep. Mm-hmm.
Here, the resonance function is a tanh. Okay. And Dirk, what you just mentioned, why do people, in fact, the first reference I know for this trick is Percy Dive's PhD, which I have read. But if you look at Dive Trubowitz, the famous 140-page paper, whatever it is, on inverse scattering, they have that in there. That's where I first saw this. But look at all these references where people do similar things. The reason that it is convenient to flip is because the D star D doesn't have a zero mode anymore. Why? Well, because D clearly would have only D y inverse is zero. So y inverse is the zero mode of D. But that grows exponentially. That grows exponentially. It's not L2, it's not L infinity, and therefore is spectrally irrelevant. That is
so you
why
remove the eigenvalue at zero.
you remove the problem at zero. But here there's a miracle that you in fact turn the potential identically into zero. And if you look at this very recent paper, they only use L2 methods, but very brilliant ones. Quadratic forms, Laplace functions, and so on. And they have a theory of asymptotic stability of the kink locally in the energy class in a moving frame because they allow their kink to move. And what they do is they apply the supersymmetric trick and they formulate a repulsivity condition, which is, Dirk, you will immediately recognize as some kind of virial condition. And
that stuff has to be pushed to infinity.
But their theory doesn't apply to sine-Gordon because then their potential is identically zero, which is what we use. And it doesn't apply to phi 4 either. It applies to phi 6. Okay. So look, there is on YouTube, I think, a very nice lecture by Martel from a few months ago where he explains that. Where he explains their theory and the fact how their repulsivity virial type condition, which is formulated on the new potential, on the supersymmetric potential, doesn't apply to sine-Gordon.
I have one more comment with the supersymmetry. There's also a very nice book, The Dirac Equation by Austrian colleague Thaler.
Yeah.
And he also shows how with the Dirac equation, where there's a supersymmetry structure behind that somewhat, and explains it in a really nice way in this book.
I see.
And I think he also says something about the origin, why it's called supersymmetry. It's sort of a much simpler version of this general supersymmetry thingy.
Nice.
But it's related.
Okay, are there any other questions, comments? Okay, maybe for the purpose of this colloquium, Wilhelm, for graduate students, let's say, who would like to follow your lead, so what would be good resources for this area?
Well, do you mean in terms of papers or books?
Papers, lecture notes, books.
Well, if you look at our paper on arXiv, you will see that we cite a number of books. The literature is huge, and it's divided into physics literature, which is numerical and phenomenological, and you don't find any proofs in there. And in fact, confusingly, in the physics literature, all sorts of conflicting and contradictory claims are made about Kinks, anti-Kinks, and so on. So I suggest just look at our paper and then go to the references. We cite some books. Only over the past 5 years have 2 or 3 books appeared, which are mathematical physics. So they are fairly rigorous. And then a very nice paper is by Laurie and Jacek Jędrzejczyk. I can't even write Jędrzejczyk. So Andrew Laurie, Jacek Jędrzejczyk, there's a J, where they look at kink and they can show the existence of kink anti-kink for phi 4 by L2 methods. No, they don't discuss L infinity asymptotic stability. And so these 2 places, which you find, both of which you find on arXiv, give you a lead into the literature and the field.
Okay. All right. Thanks again.
Thank you for the invitation.
Thank you.
Okay,
Thank you all for signing in.
Okay, bye-bye.
Thank you very much.